Welcome, this is question number 5 for AQA's A2. This is the Unit 4, Section B, okay? As I say, this is question 5. So, what we're given is this object of mass 0.25 kilograms with a radius of for God's sake, I can't even speak anymore. A radius of 1.5 meters, okay? And I've rubbed off with the velocity, but we're told that the velocity was going at a constant speed of 8.6 meters per second. I actually got a pen that works once. Okay, so you can kind of tell it's going to be some kind of circular motion equation. However, the first bit, I think this question is very once you've gone, oh yeah, that's it. Well, and I should have built up to that really. The question's worded in such a way that it's really confusing. But once you get the understanding of what the question's actually asking you, it's one of the most simplest circular motion questions you'll ever get. Okay. Now, first part A says calculate the angle in degrees through which the string turns in 0.4 seconds. You may go, how the hell am I going to work that out? Well, we've got to work out when t is 0.4. Okay. What percentage has it covered? Okay, now let's just think what we've got so far. So we've got the radius, we've got the velocity, we've got the mass. Okay, quite clearly we don't have the time period. Okay, and it's likely the time period is going to be relevant somehow. Okay, so it's a good debate whether to bring it up. Okay, so I'll give you the shorthand of what we're going to do, how to answer this question, and I'll go through how to answer it. Okay, so we can't work out, there's no way of drawing some kind of, because you might think, oh well, we'll draw a triangle, okay, and try and work out the distance of the arc it's going round. No. Well, we know we can work out what the time period is, okay. What we're going to do is work out the time period and then see, and then, as we know, it's covered 360 degrees in one time period, okay, because obviously it's gone around the full circle. So what percentage of the overall time period is this 0.4 seconds? Okay, it might be more, likely going to be, it's not, okay, but it's likely to be less than the proper time period of the full rotation, okay. And then what we need to know is how much as a percentage or as a decimal of the of this is this 0.4 of the entire time period, okay. And then because we're assuming it's a constant speed, it will be increasing, it'll be going over each angle, okay, it'll be covering the same angle per second, or whatever it covers per second, okay. So each angle will take the same time to cover, okay, so it's constant speed, so basically there's no acceleration overall. I mean, I know there is, but anyway, what essentially we're going to do is work out what the time period is, how much of that percentage of the time period, and times that percentage by 360. Okay, to work out, because we know if that was 100% of the time period, then it would cover 360. Okay, so that's in essence what we're going to do. But as I say, first of all, we have to work out the time period. Okay, now for those of you that were thinking, I would never have seen that in my entire life, neither did I. Okay, obviously until I did the question. But we have to think, well, what have we got here? We've got the velocity, we've got the mass, and we've got the radius. Now, quite clearly, it's going to be a circular motion equation. Now, what circular motion equations do we know? Okay, well, we've got F equals mv squared over r. That's quite a common one, okay? But that's not going to help us work out the time period, okay? Because, well, there's no time period in that, and the only part that relates to the time period that's in that equation is to do with the velocity, okay? And we've got the velocity on its own, so we don't need to work out that using F equals mv squared over r, okay? Because we'll just get a force, okay, and that's not going to be very helpful. So, as I say, we need to use one of the other parts of the information that we've got. Well, there's no equation for the radius, there's no equation for this, there's no equation for the mass, so it must be an equation to do with velocity that will allow us to work out the time period of it to do the full rotation, okay. So the velocity time period, okay, is 2 pi r over t, okay, or 2 pi f r, okay. But because we want to work out the time period, it's just easier to use this equation. Now we're given all the other bits of information apart from the time period. Okay, so we're given the velocity, which is 8.6 meters per second. Okay, is equal to 2 pi times the radius. Where the radius is 1.5 meters. Okay, over the time period. Rearrange to get the time period. Okay, so obviously times both sides by t, divide both sides by 8.6. shove it in your calculator. Okay, it's basically rearranging. You get the time period is 1.095, and it goes on, etc, etc. As I say, I would leave that answer in your calculator, but that is not your final answer. Okay, we know that's a time period, and in that time period, you could say that it covers 360 degrees. So for it to cover 360 degrees, it needs 1.095 seconds. Okay, so how many seconds does it need? Sorry, how many angles does it cover in 0.4 of a second if in 1.095 it covers 360? Okay, so as I say, there are different ways of converting it. You can either work out how many angles does it cover per second, okay, or how many seconds does it take to cover one angle, okay? So as I say, it's totally up to you which way you go about answering this once you've got to this stage. Okay, but what I did is I said, well, we've got the 360 degrees is the 1.05, so we need to know what percentage of this 1.095 is this 0.4. So in other words, we have to do 0.4 over the time period, which we got to be 1.095. You don't have to times it by 100, okay? But I just like to, because I'm lazy. But as I say, you could just simply, I think it looks better if you times it by 100, okay? Because you know what percentage. But you're going to have to use a decimal answer of 0.4 over 1.095 to times by 360 to get the answer. But just to show you what percentage it is, normally, as I say, with percentages you show it as times by 100, so that's why I've done that, okay? And when you do that, you get it to be 36.5%, okay? And what we're going to do, we know that this, okay, 0.4 is 36.5% of this 1.095 seconds, which is the time period. And as I say, remember, we cover 360 degrees in one time period, okay? And as this 0.4 is the 36.5% of the overall time period, the angles that it covers in 0.4 seconds is going to be 36.5% of the angles covered in 1.095 seconds, which is 360. So therefore, the angles covered in 0.4 seconds is 36.5% of 360. Now, obviously, to work out percentages, very simple. You actually need the decimal of this. In other words, what 0.4 over 1.095 is, which is 0.365, etc., etc. Okay, and you times it by 360, you will therefore get the angles covered in 0.4 seconds, and you should get that to be 131 degrees. So as I say, what we're doing here is doing this because we know this is the percentage, okay, but to work out the angles we need to make sure this is a decimal, and we're not timesing 360 by 36.5, because therefore we're covering more angles in 0.4 seconds than we do in 1.095, and that just doesn't make sense, okay? So you make sure you use a decimal of 0.4 over 1.095, okay? So you do 0.365, etc., etc., times 360, okay? And that will give you your angles of 131 degrees when rounded, okay? And obviously, depending on if you use rounded figures, you'll get between 130 and 131, okay? Which obviously, as I say, should round up to about 131 degrees. So hopefully that makes sense. The next part is using F equals mv squared, okay? We're asked to calculate the tension in the string, okay? Which is this, obviously, red thing. Now, the key thing with this, and it helps with many questions, not just this one, other ones in mechanics and, all the parts of physics. It's key to realise that the tension is a force, it's a magnitude in the given direction, so it's a force, it's a vector, okay? Which crucial for this, we don't have an equation for tension, okay? But we do have an equation for force, which is to say F equals mv squared over r, okay? Now, because this is not like the Big Dipper, this dotted line just shows its direction, it doesn't show it's going along this path, okay? That's not a path, that's just its direction, and as I say, that's different because otherwise if this was a path we'd be having reaction forces from the path, but as I say, it's just a direction, so we assume the only force acting on it is this mv squared over r. If it wasn't, okay, we couldn't assume the tension was equal to the force, okay, so you need to take into account, but as I say, that really kind of is more emphasised when you're actually doing questions, so I haven't really done it on this diagram, and I probably should have done, you need to show what forces are acting on this object. Like, where is this, in the case of centripetal acceleration and centripetal motion, circular motion, you need to show which direction the forces are acting. So, which direction is the circular motion force? Okay, in other words, F equals mv squared over r. What's the resistance forces acting that will be acting away, and is there any support forces? So they're the three forces you need to consider. But as I say, this dotted line just represents a path, okay? It doesn't represent any thing for the mass to lean on, okay? Think of it like that. So therefore the only force is equal to mv squared over r, so we can say the force, centripetal force, is equal to the tension, okay? So as I say, it's just asking for the tension, okay? So all we have to do is sub in our numbers of the mass to be 0.25, the velocity as 8.6, okay, and yeah, the radius as is 1.5. For sake, I tried to circle that, but ended up crossing it out, so I do apologise. Okay, so as I say, F equals mv squared over r, so m is this 0.25 kilograms, okay, v squared is equal to 8.6 squared, okay, over the radius of 1.5. Okay, so you just sub their numbers into your calculator. Again, very simple calculation, and you get 12.3 newtons. Okay, so fairly quite simple. But as I say, the wording is a little bit, I don't really like it. That doesn't make sense, but I don't have to make sense. Because I'm me, so I don't have to. Anyway, so the next part, after I've had a cup of tea, 1 second. It's a good cup of tea. Not because I made it and I'm an expert at that, just it is. And that's 50 quid from advertising. I wish, anyway. Right. Okay, so anyway, for 5b, it says, the string will break when the tension exceeds 60 newtons. Calculate the number of revolutions the ball makes when the tension, in 1 second, okay, when the tension is 60 newtons. Now, there's a couple of things I just want to point out before we start answering this. Obviously, that will help us answer. Okay, so the first thing it mentions about the tension, we've got to find when the tension is equal to 60 newtons. Okay, because that's the minimum number of revolutions it takes. Well, we'll go on to that in a minute. But anyway, we need to work out when the force is, the tension is equal to 60 newtons. And as I say, because we showed here that the only force was mv squared over r, and that's equal to the tension, okay? We say the tension is equal to the force, which is equal to mv squared over r, okay? So that's, again, a key statement. The next statement, okay, is this bit, what we're actually asked to calculate. Now, there's no point calculating the force, because we know that. There's no point calculating the mass, because we know that. And there's no point calculating the radius, because the radius isn't changing, okay? But obviously we need to eventually do something with that velocity when we eventually work it out. But the key thing here is the wording. Calculate the number of revolutions that the ball makes in 1 second. The number of revolutions per second. That's the frequency. Okay? So that's why I say this wording is weird. Because I'll be honest with you, I probably wouldn't have spotted that in the exam in terms of the fact that the number of revolutions was a frequency. Obviously that's easy now, but just be aware that you know what the wording of certain questions are, okay? So as I say, that's another way of saying the frequency. The time period, okay, is the time for one complete oscillation, okay, or one complete cycle, okay? So just make sure you are aware of the definitions, because they could put that as asking for the frequency when they ask for something which has the definition of the frequency, okay? Such as this, where it says, calculate the number of revolutions that the ball makes in 1 second, okay? So what we're going to have to do is calculate the frequency. But as I say, we've got this equation and all we can calculate is velocity. However, just like we did in A part 1, we use the velocity to help us calculate the time period. Now you know the time period is 1 over the frequency. Okay? Well, you've got therefore obviously the velocity equation because we're going to, all we can do with this, first bit of information, and that's the only thing we can work out is the velocity, okay? Well, I'm sure there's things anyway, but that's the main thing it's trying to get us to work out. The only thing we can use the velocity to help us answer is equal to 2 pi times the frequency times r. Or you could just work out the time period like we did here, and then do 1 over that. But this is just kind of a cheap, easy way of doing it, because we're all lazy and want to have as much time to do absolutely nothing in our lives. So, okay, so anyway, as I say, Well, in this case, when we work out the velocity, we'll know what the velocity is. But actually, no, yeah, we work out what the velocity is. We know the 2 pi f times r. Well, 2 pi is a constant, so you know that. You don't know the frequency. That's what you're trying to find out, and you do know the radius. Okay. So again, very simply, what we've got to do is work out what the frequency is when the tension is 60 newtons and when the force is 60 newtons. So basically, what we've got to do now, so hopefully you see where we're going to go from this. Okay, so F equals mv squared over r, and we need mv squared over r to equal 60 newtons. Okay, and as I say, we know m and we know r. Okay, as I say, we know m to be 0.25 kilograms, so it's 0.25 times v squared. I'm not going to put the units in because just crazy. Over r, which is, as I say, 1.5 meters, newtons, whatever, same thing, and that's equal to 60 newtons. Okay, so obviously just again of rearranging, but I'll actually do the rearranging for you. So 0.25 times v squared is equal to 60 times 1.5, or 90 newton meters. Okay, but as I say, you don't need the units, and I lied that I said that wouldn't include them, and I did, but you know, sue me. Okay, so anyway, I need a sit down. That's nice. Okay, so obviously what we've got to get here is v on its own. So v is equal to the square root of 90 over 0.25, and I think I left that as the square root of 90 over 0.25 actually, because I'm lazy. Okay. Yeah, sorry. That the square root of 90 over 0.25 is the velocity, which comes to 6 root 10 meters per second. Okay, and as I say, we know the velocity is equal to 2 pi f times r. So this 6 root 10 is equal to 2 pi times f times the radius, which is 1.5 meters. Rearrange to get the frequency. Okay, so the frequency, therefore, divide both sides by 2 pi times 1.5, or alternatively, obviously, you could just work out what 2 pi times 1.5 is. Okay, which is quite clearly 3 pi meters. But as I say, it's up to you. I just like to keep it simple because I am simple. So, anyway, 6 root 10 over 2 pi times the 1.5. Okay, and obviously that will get you there your frequency as 2.01 revolutions. Okay, so that's how many revolutions per second. Okay, now don't get confused and say, oh well, it must be 3 because we've got to complete a full revolution. Well, you don't have to complete a full revolution. I mean, maybe it's just me thinking, not thinking, oh, we'll make it more complicated than it needs to be. Don't, because I do that, and you can look what kind of a mess I am. So anyway, maybe it's a good thing, maybe it's not, but we'll see how we go on. And then I'll keep having them pauses in the middle of my sentence. Okay, so anyway, thanks for watching. That's the end of question 5. I had to sit down in that question as well. I'm going to do more than questions when I get to sit down because it's nice, it's a bit of a change. Okay, so anyway, that's the end of question 5, and we'll see you in the next question. Thanks for watching. Sorry, I thought that was the end of question 5, but due to my inability to turn over the page, like so, I didn't see the 5C. However, obviously I did see it on the mark and I've answered it, so don't worry, we'll go through it. Okay, so anyway, 5C basically is asking us to discuss the motion of the ball in terms of the forces that act on it. So we have to apply Newton's 3 laws of motion. Newton's 3 motions, maybe a bit of that and a bit of that. You get the idea. Anyway, we're asked to explain how Newton's 3 laws of motion apply to the motion of a circle, okay, and explain why in practice the string will not be horizontal. Okay, so Newton's first law, okay, says, so obviously the first, because it's got the 2 points, we need to go through all of Newton's 3 laws, okay? And Newton's first law, there's no harm in stating what it is just before you answer it, okay? As I say, Newton's first law says that an object will remain either at constant velocity or at rest if the object or the forces that act on the object are the same magnitude, okay, in opposite directions, okay? So how could you relate this to the ball? Well, obviously we know that the velocity is really changing, but So therefore that thing would be really to do with the speed, is motion, law of motion, okay? It's to do with the speed. It will remain at constant speed or at rest, okay? So you would state Newton's first law, which is pretty much what I've said. Just can't bother writing it down. So state first law, okay? And then you would say relate it to the situation, okay? And obviously we've got a ball where the rope, the tension in the rope is towards the centre, and any resistance force is obviously trying to pull it away. So you would say therefore because the force is, you'd say because of the centripetal force equals the resistance force, which I'll say, and you would state the direction of both. Okay, and you say because they are equal, okay, this means the object is at a constant speed. That's key. So constant speed. Okay. The second point, obviously, we're there for the second law. Okay. Now the second law states that F equals ma. In other words, resultant force is equal to mass times acceleration. Okay. Now this is quite a weird one, because I mean I kind of explained it in two separate points, okay? I built up to stating the second law. I know I've kind of put it here and state the second law and then explain it, okay? But what I kind of did was said why there was acceleration, okay? So, maybe that's first law wasn't brilliant. I think I'm probably going to contradict that first law, so I do apologise. I think I've done something wrong. Yeah, because what I'm going to say is obviously there is a resultant force, which this point suggests there isn't. So maybe that first point wasn't so accurate, so I do apologise about that. But just going to leave it there because I've probably done something wrong. Okay, so anyway, you would say, because there is you would say as a velocity, so you would explain why, so for explanation of the second law, you would say why the velocity of the object is increasing even though it's going at a constant speed. Okay, so you would say because, you would say that as a velocity is a vector, it takes into account magnitude and direction, okay? Now, the magnitude stays the same, but direction is increasing, so therefore the velocity is increasing. And if the velocity is increasing, okay, over a given period of time, whatever time you measure, okay, therefore this implies there is acceleration, okay? So, even when the object is at constant velocity, okay, then you would go on to talk about the fact that the acceleration acts towards the centre, and you would relate that to the force, centripetal force, okay? So as I say, you would relate acceleration, so therefore you'd say as acceleration equals v squared over r, and F equals ma is equal to F equals mv squared over r. If the acceleration is increasing, we assume the radius to be the same, okay? So therefore the velocity is increasing, so therefore there is an increasing resultant force, okay, or there is a resultant force, sorry, not increasing, there is a resultant force, which means the centripetal force is bigger than the resistance force, which is not what makes me think all of that is wrong, but I don't see why it would be. But anyway, yeah, maybe not. Anyway, so you say there is a resultant force, so therefore, yeah, so that applies, obviously, to F equals ma, Newton's second law of motion. Okay, Newton's third law of motion is that for every action there is an equal and opposite reaction. Okay, so this is for that, because I didn't mention that. The ball must be, it says here, the ball must pull on the central point of the support with a force that's equal and opposite to the force from the centre. Okay, which kind of makes me think, yeah. Yeah, the third law is very similar to the first law. I think I've kind of explained this one. Yeah, so this bit here where it said centripetal force is equal to the resistance force, that's kind of the same explanation what you would put for the third law. Okay, so I do apologise, I've not explained this question very well.